Okay, so today we're going to talk about uh, planetary energy balance. So we've talked, for example, we had the Daisy World model, which simply used albedo of one plant as the main thing that was affecting, through feedbacks, the habitability of the planet. So the next part of the course, we're going to talk in more detail about the greenhouse effect, solar flux, and the physics and processes that help regulate the climate on Earth. In more detail in the real processes, not just imaginary daisies. So we're going to go over a number of, some of this might be review, but a number of important concepts and processes that we need first to have that conversation. So we'll be talking about waves, electromagnetic radiation, solar flux, and black body radiation today. And so we could say we're talking about planetary energy balance and the greenhouse effect. I'm not going to get into that in this lecture, but soon. We can call this, this will be part one of several. And for this lecture corresponds to a reading, page 34 to 41 in the same book that we've been using for the greenhouse effect, the carbon cycle chapter. Okay, so we'll start by talking about electromagnetic radiation. And this is a topic that is relevant, and I'm going to abbreviate this EM. Electromagnetic radiation is a topic that it introduces a lot of things that are relevant to a variety of other aspects of the sciences. For example, we'll talk about waves quite a bit, and waves are something that we see in all different parts of the Earth, and for example, earthquakes being seismic waves or causing seismic waves. Remote sensing, like tools that we use to measure the Earth, are all part of this all part of this category of waves. So we can think of, in this case, we're kind of aiming at the greenhouse effect. So we're going to talk specifically about electromagnetic radiation. You can think of this as an electric and magnetic wave. And these sorts of waves, this sorts of radiation, so radiation meaning an energy transfer, so that's another topic that we'll be exploring in more detail, how things, including energy, move from place to place. So electromagnetic radiation includes light, visible light, ultraviolet, which will be abbreviate UV, infrared, radiation, which will abbreviate IR, and many other things that we're not going to talk too much about. Microwaves, radio waves, X-rays, gamma rays, they're all in the same spectrum of electromagnetic radiation, but we're going to be focusing for the greenhouse effect mostly on visible light, UV, and IR. So this sort of radiation moves at the speed of light. fixed speed, which we're going to abbreviate, we'll just call it c. And that speed is 3 times 10 to the 8 meters per second in a vacuum. And of course it changes if it's going through water or some other material. And of course, since it's a speed, the units here, we have a length over time. Okay, and the other properties of electromagnetic radiation that we're going to focus on, wavelength, and this is a property of any wave, and we'll abbreviate it lambda. Wavelength is the distance between two crests. So a wave might have a shape like this. This could be the electric or magnetic component. And this distance, we refer to the top of the wave as the crest, but you could use the troughs. It depends on your perspective. It doesn't matter. Any repeating points like this, that's the wavelength. So, and this has units of length, right? It's a distance. And this wave is moving, right? But that distance isn't going to change. Okay, and the other property of the wave that we need here is frequency. We use the Greek letter nu. And the frequency is the number of crests that pass by in a second. So this has units. So it's a number of something per second. So it's going to have units of inverse time. So if we're standing here and this wave comes by, we could count the number of times the crest happened per second. So this is these are related, right? The frequency, the wavelength, and the speed. And together, they define a wave. So there's other things like polarization and other things and amplitude that can be important for a wave, but these are the sort of the most basic elements. And like I said, they're related, and I want you to pause the video next and see if you can figure out what the relationship between these is. It's an equation with these three variables in it, and see if you can work out what that equation is about to be. So pause the video now. Okay. So there's different ways you could approach this, but a very sort of a pretty reliable way would be to look at the units. Okay. So you can see that if we were to divide the wavelength, if we were to multiply the wavelength by frequency, we'd have units of length over time. And that's going to be that's actually going to be the formula. Wavelength times frequency equals the speed. And the units work out for that. And another way to approach this is these are essentially an analog to the equation of motion that you might have seen. So distance equals rate times time. Hopefully that one's managed to stick in my head all the way since high school. So this is basically the same thing here. So we have the time-related term being frequency. So it's the inverse of that. The rate being the speed of light, and then the distance being this length term, right? So it's basically that distance is rate times time equation, but for waves. So that would be the distance being the wavelength equals the rate, should be c, and then we need to, to get the units right, we're not going to times it, we're going to divide, or we could say times 1 over the frequency. All right, and since the speed of light is constant, lambda and nu are inversely related. So if this is review for you, I would challenge you to try to get this to the point where you remember it without looking it up. These relationships, or you're able to maybe not remember it, but you can think it through. So thinking, for example, starting with the motion relationship, you could work out, or thinking through the units, you could work this out. That would be an indication that you've got it down pretty good. Okay, so in other words, right, so if we look at this is a constant. So if we have a large wavelength, we are going to have a small frequency. That kind of makes sense, right? If this thing is moving at some rate, we can imagine like this crust is moving at this speed, but these are far apart, then not very many crusts are going to go by in a second. But if the wavelength is really small and they're going at the same speed, it's going to have a high frequency. So that's encapsulated by this relationship here. Okay, so visible light is a wavelength between around 400 and 700 nanometers. These are just some sort of important factoids. In terms of the sun, about 40% of sunlight is in the infrared spectrum. So let's talk about this for a second. Okay, so color, when we see color, of course, it's a function of the wavelength. Our eyes have evolved to detect differences in the wavelength. Color of light is a function of the wavelength. And red is longer. So the reds are in the sort of the 700 range, or that end of the spectrum, and the blues shorter. And that means that the blue is a higher energy. Well, we'll get to that. We'll get to that in a moment. Okay, so we have like reds here, blues, and then so infrared means like beyond red, right? So that's going to be off at longer wavelengths, and then UV, ultraviolet. It's kind of like blue, red, orange, yellow, green, blue, violet. So it's off on this end, right? So the light coming out of the sun, which is important for where we're going here with in terms of the energy balance of the planet, about 40% of that is infrared. So this is the wavelength of around 1 micron to 1 millimeter. So 1,000 nanometers is equal to 1 micron. So just to be complete, a micron is 1/millionth of a meter, and 10% of the sunlight. So of course, the visible light is about half of what we get from the sun. UV, sort of, this is the 10 to 400 nanometer range. And a nanometer is a billionth of a meter. Okay, so 50% of sunlight is visible to humans. And we'll come back and talk a little bit more about UV and IR later in this lecture. So the energy, so we can think of light as a wave, of course, and also as a particle, as you guys know. So we're going to need to think about both of those things here when we talk about the greenhouse effect. So the energy of a photon, which is the light, sort of the electromagnetic particle way of thinking about it, we'll call that energy E, is equal to a constant called Planck's constant times the frequency. Or if we use the equation from above, the Planck's constant times the speed of light, which is also a constant, divided by the wavelength. So h is Planck's constant. It's around 6.63. It's 10 to the minus 34 joule seconds. All right, so let's see if the units work out here. Okay, so joules are a unit of energy. So we would expect, when we check the units here, that we should have joules on the side of the equation. So, right, and we have Planck's constant, we have joule seconds, and we had frequency was measured in 1 over time, 1 over second. So yeah, so the units check out. So what this means here is that the shorter the wavelength, so if we have a short wavelength here, we're going to have more energy. And that actually makes a big difference for molecules. So if you think about when we go out in the sunlight, we're worried about UV. People that are, not everybody, but people that are influenced by the sunblock industry are worried about the UV light, or maybe you wear sunglasses that block UV, because that's the stuff that has more energy. It's more damaging. Infrared, you can buy an infrared sauna, right, to bathe yourself in this, just feeling the heat. But it's not really, it kind of just shakes up your molecules. It doesn't break it's not going to break them apart. So the higher energy stuff hits them hard and can cause more problems. So when we get to really high energy, we have X-rays and gamma rays and stuff that can penetrate into living tissues and so forth. And I think you can remember, I think based on for me, a way to remember which, to come up with it, to remember which is the higher energy, is thinking about that, the UV being the thing that people are trying to block. Okay, so another topic, the next topic that we need here, we're going to come back to this, the energy delivered by the sun, it is measured in terms of flux. And we talked about flux before, but we're going to define it a little bit more quantitatively here. So a flux is an amount of stuff per time per unit area. So here, we could talk about the flux of water through a river. And here we're talking about, for stuff, we're going to talk about the energy. So flux, flux we're going to have, we're going to really pay attention to units here. So flux will be, some energy, and it says per time, per area. So this will be, should say, length squared. So we talked before, energy units were joules. So a joule per second per meter squared. And some of you might remember that joules per second has its own unit. It's a watt. So units of flux could also, for energy, could be also watts per meter squared. Watts a joule per second. And that makes sense, right? Okay. If you think about some everyday things, so a light bulb is measured. When you buy a white light bulb, you can get a different number of watts. And it used to be the old-fashioned light bulbs, like a 60-watt light bulb or a 45-watt. So that's a measure of how much energy is coming out of it per second. When you pay your energy bill, it comes in the units of kilowatt hours, right? So a kilowatt, right, obviously 1,000 watts. So why is it kilowatt hours? So the energy, the electric company is telling us about the total amount of energy we use over some amount of time. So that's going to be taking the joules per second times some amount of time. So that's going to get us back to the energy term. So kilowatt hours is really, they really should just say joules. But maybe people are a little bit more familiar with watts. So that's what they do. Solar flux, which we've talked about, like for example in Daisy World, but we didn't get into this detail. The solar flux depends on how far you are from the sun, right? If you're right next to the sun, it's going to be pretty high. But where we are here at Earth is around 1,370 watts per meter squared. Okay, and that distance, or that flux, as I mentioned, varies. As a function of distance from the sun. So the energy reaching any celestial body, including Earth, it varies as what's called the inverse square of distance. And so the formula, I'll just write it and then I'll talk about it. Okay, so S would be the solar flux at some distance r, and then S naught would be the solar flux at some reference distance So if we were to take a reference, just to sort of think about this, so if we took a reference distance as 1, so a solar flux, if we just said whatever the flux is, we'll just call it 1. We do that at a distance of 1, and Earth, the distance between Earth and the Sun is also called an astronomical unit. So if we were to compare, let's use Earth as the reference, okay? If we were to go to, for example, twice as far away from the Sun, so we use r as twice the reference distance, we get S solar flux being 1/4 of what Earth gets. And same thing if we were to go 3 times the distance from Earth, so go Earth's distance from the Sun and then do that twice, 3 total, we get 1/9 what Earth gets. So it dies off pretty quickly the further you go away. And it goes as you can square this number 2 or 3 and then and 1 over that. So that's why it's called the inverse square. And it has to do with, the reason it's inverse square is, if you think about something emitting energy in all directions, it's getting spread out, right? And you could think about it as like, it's 3 dimensions, so the surface area of a sphere is 4 pi r squared. So it comes from this square term there. So all the energy that's coming at this point in time, there's a certain amount of energy, and when you stretch that out to some later point in time, it's the same amount of energy, but it's been stretched out into this much larger space. And so there's some implications of this, probably to first order explain, okay, we're looking at our near planets. Venus is really hot. Mars is cold. And this has a lot to do with this relationship here. But the Earth's climate is sensitive enough that even so the orbit of the Earth has some, it's not uniform over time. So there's small variations where it spends some time at further distances than other times. And those have been calculated, and they line up with the glacial and interglacial periods. So even, they're called Milankovitch cycles. Right, so even small variations in relatively small, within the orbit of a single planet, the fact that the distance is squared makes a big enough difference that it can have major implications for climate. Okay. So the next topic here that's relevant for energy flux and trying to understand how the climate of Earth maintains a relatively constant temperature is this black body radiation. So everything, suns, planets, you, me, we are emitting electromagnetic radiation at all times. And so, sometimes this is really obvious. We see the sunlight, but try to think about it. Think about that whole spectrum, right? Particularly infrared, ultraviolet. So, when if you heat up your stovetop, you can feel, you put your hand near it, you can feel the heat coming off, right? Even if it looks the same. If you turn it up, I have an electric stove, so if I turn it up high enough, it starts to glow red. So at that point, it's emitting radiation that's visible. It's in the red wavelengths. But even when I can't see it, I can feel that heat coming off. This is the same. Our eyes just happen to be able to detect this in a certain range, but there's nothing fundamentally in terms of physics different between that heat coming off that we can just feel instead of see versus the light we can see. Infrared goggles are another example I like to think about, right? So, if it's super dark outside, my eyes can't see it, but I put a detector on, I could look around and I could see things that are warm are going to glow, and the goggles have been tuned to be able to detect infrared light. Because the warmer the things are, the more radiation is coming off. We'll talk about that next. So hotter things, this is kind of intuitive. Just a minute. Hotter things emit much more electromagnetic radiation. Okay, so fundamentally, there's not really any difference between you and me and the sun in this case, except that the sun just emits far more energy, and it's proportional to the temperature. So the relationship there is the flux of energy coming off a black body is equal to some constant times temperature to the fourth. Okay, so that's why it's that's why the sun is emitting tremendously more energy than you and I, because of that 4. So sigma is called the Stefan Boltzmann. Actually, I think it's called the Boltzmann constant, but don't quote me on that. This relationship is called the Stefan Boltzmann law. -8. And units there are watts per meter second per Kelvin to the 4th. And it's useful to think of a thing called a black body. So a black body is something that emits and absorbs with 100% efficiency. Okay, so right, like black things, we see. If we see something that looks green, it's because there's light with the wavelength that looks green to us. That energy is coming into our eyes. So things look black when they're not emitting visible light. They look white when all the different detectable wavelengths are coming in. Okay, so black body is something that sort of perfectly absorbs and perfectly radiates according to its temperature. And relationship looks like something like this. So we'll have wavelength. So black bodies, which are a pretty good approximation of everything. Radiative flux. So they emit over a spectrum. This looks kind of like this. So there'll be this is the dominant wavelength, and that's related to temperature. So the peak This is called Wien's law, and I might be pronouncing that wrong. So temperature here is in kelvins, and the wavelength in microns. So if we know the temperature of an object, we can predict what the wavelength will be dominant, and we can also predict this whole function. This is called the Planck function. And the Planck function, basically, it's just telling us the intensity of electromagnetic energy, how it's related to wavelengths. So this is a really useful. Astronomers use this all the time. You can look at look at the spectrum of the energy, and they can figure out how warm a star is, for example. So some examples. So the sun's temperature is around, at the surface, around 5,780 Kelvin. And so if we use this relationship here, the peak wavelength is around 0.5 microns, which is 500 nanometers. So that's visible. That's in the visible light spectrum, as we wrote above. This would be like a bluish green. And we call that, in terms of when we're thinking about the greenhouse effect, we call that relatively short wavelength. And that contrasts with the energy that the Earth is emitting. So the Earth's surface temperature is around 15 degrees Celsius, or around, which is 288 Kelvin. So that the wavelength from this relationship that's peak is around 10 microns. So this is in the infrared spectrum, and we call it long wave radiation. And as we'll see, the energy, if we think of the Earth, right, it's getting this flux of the sun's energy coming in at short wavelengths, and then it radiates according to its temperature, which is going to come out as long wavelengths. So figuring out understanding why the Earth has the temperature that it has is going to involve a balancing of these sorts of energy wavelengths. All right, and I'm going to show you a little website illustration that shows this nicely. But before we do that, let's look at the same plot again. So we have wavelength, we have flux, and let's put some numbers on it this time. 0.01, 0.1. So, right, Earth peaking is going to peak around 10, right? So it's going to look something like this. And the sun, wavelength, let's put units here of microns. So the sun is around 0.5 over here, right? The other thing is, right, the flux, we're going to measure on a log scale because of this huge magnification based on the temperature, the power of 4. So obviously the sun is emitting tremendously more energy than the Earth is emitting. So we measure this as each of these is a factor of 10. So we got 100 all the way up to around 10 to the 8th. I didn't draw enough ticks, but so the sun is peaking around 10 to the 8th in terms of the energy it puts out. And this should be flux measured in, right, watts per meter squared. Okay, so a couple things to note here. Well, one is the area under the curve is the total energy that's emitted. So let's label. So this is the sun. This is Earth. So area under curve is the total energy flux. So you can see that, so even though the sun emits its peak wavelength is quite a bit smaller in an invisible range, it still emits more energy in the infrared spectrum than the Earth does. Let's go to a website where we can kind of play around with this relationship. So, okay, so here we are, the same plot, and they've colored the visible spectrum here, and we can select different things. So the sun is here, the Earth is down here in terms of the temperature. And when we change the temperature, we affect that curve, right? So the curve, if we go down to Earth, at the scale, we're not even close to Earth, right? So at the scale, this is this 10 to the 4th issue here. We have to really zoom in. So we started off with the sun. We were at 100 megawatts per meter squared. So we're down, zooming in, we're down at like 0.8, and we're still going to go down here even more. We still can't get close enough. Must have pushed the wrong. No, let's go. What's happening here? I need to zoom out. I need to go on this axis, right? Okay, here we go. Okay. Here we are, Earth. Right, we're compared to the here we go. Okay. You could see how far we had to magnify it to be able to see the amount of energy compared to the sun. A light bulb's interesting. So this would be okay. So light bulb. This would be a a traditional light bulb, not the LED light bulb. So that's worth thinking about. So a typical old-fashioned light bulb, right? So we got rid of old-fashioned light bulbs because they were inefficient. And what that means, inefficient, was basically they were generating a lot of energy, a lot of electromagnetic radiation that wasn't visible. So all this stuff was coming out of light. That's why the light bulbs felt hot, right? That's what this is. So the technology of the LEDs or other efficient light sources is they don't follow this black body curve, right? They can sort of just emit light within these wavelengths without sending a lot of energy out that we can't see. So let's go back to the sun and let's compare it to another star. So Sirius A is a star that is quite a bit hotter than the sun. So it means it's going to emit more energy. We can see that as the area of this curve is getting bigger as we increase the temperature. So at around 10,000 Kelvin, the temperature of that star, and we can see it emits some visible light, but a lot of it is off in the UV realm, right? So it's not a coincidence that our sun, most of its energy is energy that we can see. Animals have evolved in the solar system to detect things using what's the wavelengths that are most dominant in the environment that we're in. But if we were a planet circling Sirius A, you could imagine that we would have some kind of detection that allowed us to see in the ultraviolet. Of course, the ultraviolet light also being much more damaging to material. It's a little hard to imagine how life would survive in those conditions, but who knows? Okay, so that's about. I think that's the end of the lecture here. You can get to this. This is a SIMS. If you Google phetcolorado.edu, you can find this relationship, and you can also play around with. You can get the different values. You can see ultraviolet, visible, infrared energy, and you can calculate the area under the curve, the total amount of energy that's distributed over the different wavelengths that are emitted.